Dear students, hope you are fine. Today we are going to discuss about one of the gas law, which is known as Graham's law of diffusion. You know that this law has been described in second part chemistry under the chapter environmental chemistry. So the title of the law explains that this law is actually considering the case of diffusion, and according to our syllabus, this law has been described considering gas molecule. So before going to the brief discussion about the Graham's law of diffusion, so let's see our learning outcome from this lesson. So the statement explains that, or from this slide you can see that we will discuss or we will learn what is diffusion, and the difference between them. And our main lesson is Graham's law of diffusion, and we'll learn about different application of the law, mathematical problems, and finally we'll share some question which will help us to check our learning on this concept. So let's start with our discussion on diffusion. What is diffusion? So diffusion explains the spontaneous migration of molecules from a region of higher concentration into a region of lower concentration. So let me write the statement here. So we can say diffusion is spontaneous migration of molecules from a region of a higher concentration to a region of lower concentration. At a particular temperature and pressure. That means keeping temperature and pressure same, if we keep some material, then we can see the movement of molecules from a region of higher concentration to a region of lower concentration, and it is considered as diffusion. And the definition indicates that diffusion is a spontaneous process. And why diffusion takes place? Due to concentration. Because you can see it is moving from higher concentration to lower concentration. You can see we have placed a figure where molecules are coming from the cup. That means if we keep a cup of tea, then you can feel the smell of the caffeine from a long distance. And this type of migration of molecule is considered as diffusion process. So we can check some more information on diffusion in our next slides, where you can see this is the definition I shared earlier. It is a spontaneous process and molecules migrates from higher concentration to lower concentration. And diffusion is a spontaneous process, as I discussed earlier through my statement, and it is a slow process, and it can be influenced by temperature and pressure change, because if we increase the temperature, then molecular motion increases, rate of diffusion increases. And diffusion means spreading out of molecules all around. That means if we place any material on a table which has a particular smell, we can feel the smell all around the table. Or if we place one drop of dye and a glass of water, then you can see it is spreading out in all direction. So we can say diffusion is spreading out of molecules in all direction from a region of higher concentration to a region of lower concentration. And it happens because of concentration difference. Here some more example of diffusion. You can see it can be happened inside the cell also. Diffusion across cell membrane, you can see before diffusion the concentration and after diffusion the concentration. So there was concentration difference inside and outside. Now you can see it is almost same. Another example in the right hand figure, you can see dimolecules are spreading out. So you can see here the concentration level, and this is intermediate and this is the final level. Now we want to learn about effusion. Effusion by definition is a process where molecules will move from a region of higher pressure to a region of lower pressure. And like diffusion, this is not a spontaneous process. You need to apply pressure, and then molecule will move through a porous plug from a region of higher pressure into a region of lower pressure. But it is faster process. And like diffusion, it can be influenced by temperature and pressure. Unlike diffusion, we can see it is spreading at a fixed direction, because we know that diffusion takes place in all direction. So you can see from this discussion of diffusion and effusion, we can mark some difference between them. Spontaneity. From the definition, we can see diffusion is spontaneous, but effusion is not spontaneous. There is a difference in terms of velocity in diffusion and effusion. Velocity of diffusion is slow, but effusion is fast. Direction, diffusion all around, but effusion in a particular direction. Diffusion takes place in a medium, that means in a particular room temperature and pressure. If we keep any material, it can spreading out in all direction from a region of higher concentration to lower concentration. This is diffusion. But for effusion, you need to make pressure difference. So whenever we keep aerosol inside a container, then the pressure inside the container is high and outside the container is low. So if we press the lever, the molecules will come out from a region of high pressure to a region of low pressure through a porous plug. It will be effusion. You can see this figure. So this is effusion, molecules are coming out through the porous plug. And reason why diffusion takes place, the reason shows that diffusion is due to concentration and effusion is due to pressure. So students, we have learned about the diffusion and effusion, and now we can keep our focus on Graham's law. So although the law is defined in terms of diffusion process, but we can apply the law same in consideration of effusion. And the statement explains that whenever we will consider Graham's law, the temperature and pressure should remain constant, and the rate of diffusion of gas are inversely proportional to the square root of their densities. So mathematical relationship is like this. If we consider R is rate of diffusion and D is density of gas, then R is inversely proportional to D. So square root of density. So we can show here the concept of the law like this. If we consider R is rate of diffusion is R, and D is density of gas. Therefore, we can write R 1 by root over D. So rate of diffusion is inversely proportional to square root of density of the gas at a particular temperature and pressure. And in order to explain the concept for different gas, we can consider like this. Rate of diffusion for gas A is related to its density, from which we can write RA equals to K into 1 by root over D. This is equation number 1. And for gas B, we can write RB equals to K into root over dB. This is equation number 2. And therefore, dividing equation 1 by 2, we can write RA by RB equals to root over dB by dA. So if we know the density of two gases, we can compare their rate of diffusion. And this mathematical relationship will help us to know the diffusion rate of two gases. So from the definition and mathematical explanation, we can find some key features of the law. One is this law can be applicable for gas and liquid, and in some cases, even for solids. But in this chapter, we are actually applying this concept only for gases. And the condition for this law is temperature and pressure should be constant. And this law was represented by Thomas Graham in 1848. And it explains the relationship between rate of diffusion and density of gas. Now the question is, how will you measure the rate of diffusion? There are two options to measure the rate of diffusion. One is amount gas diffuses per unit time. So you can see in the first figure, two balloons were filled with gas, and if we remove the seal, then we can see gas molecules are coming out from balloons, but they are coming out with different rates. So number of gas molecules coming out per unit time will be helpful for calculating the rate of diffusion. For example, we can write like this: rate of diffusion R equals to V by T. That is T for time required for that diffusion, and V is the volume diffuses per unit time. So volume of gas molecules diffuses, and this is time. So this is how we can calculate rate of diffusion. And another way of measuring rate of diffusion is distance traveled by gas molecules per unit time. So whenever we keep these gases at this site and at this site, and then this molecule will move from this side to this side, and this one will move from this side to this side. And after a particular time, so they will meet at this point. Then time and the distance traveled. So this is how we can also calculate the rate of diffusion of gas molecule. So this is how we can calculate how diffusion or effusion can be calculated for gas molecule. So student, you can see Graham's law of diffusion is actually considering the diffusion of gas molecule, but according to the law, we can see rate is inversely proportional to density of gas. So if we consider two gases like oxygen and nitrogen, we do not know their density randomly, but we know their molecular mass. You know that mass of oxygen is 32 gram per mole and nitrogen is 28 gram per mole. But randomly, we do not know their density. That's why using the concept of Graham's law, we can derive an equation where we can make the relationship between molecular mass and rate of diffusion. So let's start. So from the law, we can say from the concept of Graham's law, R 1 by root over T. And for two gases, we have derived earlier, Ra by Rb equals to root over dB by dA. So density is mass per unit volume. Therefore, for gas A, we can write dA equals to Ma by V and dB equals to mb by V. And if we input this information here, then we can write Ra by Rb equals to root over mb by V, ma by V and mb by ma. So finally we can conclude like this: R is inversely proportional to molecular mass. So this is the statement which was given by scientist Graham, where the relationship was inverse. Similarly, we can find the relationship with molecular mass is also inverse. And now it is easier for us to understand which gas will diffuse first, because we know the molecular mass of gases. And thus we can say nitrogen mass 28 gram per mole, oxygen 32 gram per mole. So the diffusion rate of nitrogen will be faster than oxygen. And this calculation is also shared with you in our next slide, where we can see the same mathematical calculation. Rate of diffusion is inversely proportional to square root of molecular mass at a particular temperature and pressure. Now, what are the applications of this law? So Graham's law provides a basis for separating isotopes by diffusion, because you know that isotopes have different mass, and due to mass difference their rate of diffusion will be different. So we can easily separate them. We can make a comparison of rate of diffusion or effusion. We can find out the ratio of rate of diffusion. We can compare the known gases. We can find out the molecular mass of unknown gases. So comparison of diffusion rates between gases. We can start some mathematical problem where you can see the application of Graham's law. So this is a mathematical problem where you can see at 25 degrees Celsius temperature, 100 ml carbon dioxide gas takes 15 minutes to diffuse. Same amount of unknown gas takes 19 seconds to diffuse. Find out the molecular mass of the unknown gas. So what are the given information here? So given that we can see volume is 100 ml, and for both gases it is 100 ml. And at 25 temperature, carbon dioxide gas takes 15 minutes to diffuse. So time for carbon dioxide is 15 minutes. 15 minutes, and same amount of unknown gas takes 19 seconds to diffuse. So unknown gas is taking 19 seconds. So 15 should be converted into seconds, because the second term was in second. So unknown gas, and now we can apply the concept rate of diffusion of carbon dioxide divided by rate of unknown gas equals to root over m unknown divided by m carbon dioxide. And now volume is constant, so V by T carbon dioxide divided by V by T unknown equals to root over m unknown divided by m carbon dioxide. So VB will cancel out. Finally, T unknown divided by T carbon dioxide equals to root over m unknown divided by m carbon dioxide. So T unknown is 19 seconds and T carbon dioxide is 900, and root over m unknown divided by this is 44, and if we solve you will get the molecular mass of unknown. So this is how we can calculate the mass of unknown gas using the concept of Graham's law. We can solve another problem using this concept. Compare the rate of diffusion of carbon dioxide and ammonia at a fixed temperature and pressure. So temperature, pressure is fixed. So we can solve a problem using this concept. So write carbon dioxide and ammonia. R carbon dioxide divided by R ammonia will be root over M ammonia divided by M carbon dioxide. Therefore, R carbon dioxide will be R ammonia into root over ammonia divided by carbon dioxide. So R ammonia into 17 divided by 44. So this calculation will give you the idea. So what will be the rate of diffusion among carbon dioxide and ammonia? Which one will be faster, which one will be slower? We can get it from their molecular mass, but what is the exact amount can be obtained from this relationship. And another problem we can solve using this concept is like this. A gas tube of 2.5 meter long. So from the statement we can see this is the gas tube. If we consider the statement, it is said it is 2.5 meter long and 50 ml and unknown gas was placed at the left end. So this is the side from where unknown gas is placed. So unknown gas is here and same amount of ammonia is placed from right hand side. After 3 minutes, ammonia gas traveled 1 meter distance to meet the unknown gas. So 1 meter, if we consider this is the distance traveled by ammonia, and this is in 3 minutes. In 3 minutes. So this distance will be 2.5 minus 1 equals to 1.5 meter. Therefore, we can write the equation like this: R unknown divided by R ammonia equals to root over M ammonia divided by M unknown. So R unknown will be distance traveled by it divided by time, and distance traveled by it divided by time equals to root over 17 divided by M unknown. So we can write 1.5 equals to root over 17 divided by M unknown. And this is how we can find out the mass of unknown gas. And you can see this is another example of the application of Graham's law. So Graham's law of diffusion helps us to do many calculations. And now the students, you can see we have shared what is diffusion, effusion, and what are the application of Graham's law. Now we can share some question for you to study as the learning check of this lesson. So from this lesson, you have learned that the gas with higher mass will diffuse first. So you can compare the diffusion rate between helium and carbon monoxide. And you can make the relationship between reverse osmosis and diffusion. So do you think that diffusion and reverse osmosis is same? So just try to consider your understanding and find out the answer on it. And then in between HCl and methane, which one will diffuse first? So you can find it and you can explain also. Will you be able to find out the gas that will diffuse faster than the other one, carbon monoxide and nitrogen, or carbon dioxide and nitrogen oxide, nitrous oxide? And now for your better understanding, I have kept 3 mathematical problems here. So please try to solve it using the concept that we shared today. It will help to enhance your mathematical skill, and it will also help to understand you know about the application of Graham's law. So thank you, dear student. Stay safe, stay at home, and continue your study. So see you in our next lesson. Thank you. Bye.